think,
Right.
from outside. So you're very special.
Thank you. Thank you.
From outside as well.
Okay.
You're like the special one. And so this Maximilien Peroux from University of Pennsylvania, and he's going to talk to us about Topological Hochschild's homology for twisted G rings.
Thank you very much. Thanks for the invitation. It has been a great pleasure to be here so far. So this is joint work with Gabriel, Angelino, and Mona Merling. And I like giving this talk for several reasons. The first reason I like giving this talk is that it has nothing to do with my PhD thesis. And so it's a very refreshing setting for me. And another reason is that this is joint work. This is a work in progress, sorry. And so every time I give this talk, I always say something new and new results, so I don't get bored every time I talk about it. So today I want to talk about a variation of Hochschild homology, which has a different input and different type of output. Since I'm not sure everyone is entirely well known of what is Hochschild homology, I will first motivate of what is Hochschild homology, because otherwise you will not care for the variation of Hochschild homology if you don't even know what that is. So, so I want to talk about first of what is Hochschild homology. And of course, there are different ways to motivate Hochschild homology. I chose a certain point of view. And here's the following. So let's forget about Hochschild homology for a second, and let's remind ourselves of a very basic fact. So let's K be a field, and let A be a K algebra. So as you know, I can have a module, a right module over A, and a left module over A, and I can define its relative tensor product. So far, so good. And what is that? It can be defined as a certain co-equalizer, where I co-equalize the two actions of A on N. So that gives you a bifunctor on A, and then you go to K vector spaces, K modules, and that functor is right exact. So the problem is that it doesn't preserve kernels. That's nothing new to you guys. And so we can left derive it. And we can talk about derived tensor product of M and N. And this is equivalent to something called the bar function. It's a two-sided bar construction. Bar complex, I guess. Where I don't fully remind, but the homology of a chain complex will be a Tor. Of M and N. So hopefully everyone's familiar with this. So what happened is that we had a construction and we derived it and we tried to really co-equalize. This is co-equalizing in derived way the action of A on M and N. So now, instead of being in this context, let's consider a bimodule. Now, consider M to be a bimodule over A. Then recall that these things are the same thing as, what did I choose? Modules over A tensor A up. So the reason for that is that the left A module is the same thing as a right A up module. And so I'm kind of transferring the right A module as a left A up module here. So that's what I'm doing. And for convenience, let's just call this A tensor A up. And so I can view now left and right modules as just a left module over this enveloping algebra, as we call it. And now we can more or less ask the same question. Can I define a derived tensor product, but over the enveloping algebra? And that basically is Hochschild homology. So now we can derive the process of A, L, A, E, M, right? So I can view M as a left AE module, and A is always a bar module of itself. So that is precisely Hochschild homology, where now if you want, it would be the homology of this chain complex. So it is the Tor AE star of AM. And in general, we call the Hochschild homology of just A to be the Hochschild homology of A. All right. So essentially, that's what Hochschild homology is. And I just want to mention that you have another way to see this. So using the don't count correspondence, instead of describing for you what this chain complex is, I'm going to describe to you what is its corresponding superficial module. So the don't count correspondence says you have an equivalence of categories, or magomorphism even, between chain complexes and superficial modules. And so this thing here lives here, but I'm going to describe this object in here instead. All right. And that object something like this, where the multiplication, the faces of that superficial object is given by multiplication. So the top is just given by multiplication, but here you twist it and then you multiply. So here you have AB going to AB, or the second case is AB going to BA. That's essentially what it is. And you do the same thing for the higher processes. So you do pair, you associate 2 by 2, and the last one you multiply with the first one. And the degeneracies are given by the units. Okay. So that defines for you Hochschild homology. So why is it important? So this is a useful approximation of K-theory. So you have what's called a Dennis trace, which for any range R, you can associate, I guess I use A, so let's get it. You can associate what's called a Dennis trace, which is a direct generalization of trace of a matrix, really, if you really look down at such a level. But the point is this is very difficult to compute but has extremely useful information. Whereas this is much easier to compute. It's a Tor object, right? And so many of the computations that we know from K-theory actually come from our knowledge of the Hochschild homology and this approximation that we have. So hopefully that fully motivates you to be interested in Hochschild homology. Let me mention that so far what I've been doing was in the setting of vector spaces over, the tensor product over K and the field, but you can change that setting to spectra. I don't know how everyone is comfortable with spectra in this room, but essentially this is a larger, I like to view this as a larger modal symmetric modal category where everything you know about usual algebraic setting can be extended in a homotopy coherent way. There, it's also as a number. I don't want to be fully precise, but we call THH, so topological Hochschild homology, is just exactly this special complex, special object, defined in here. So let me say precisely what it is. THH of a ring in spectra is the geometric realization of this. So let me just rewrite the same thing. You can define in a very similar way the same faces and degeneracies. And so you get a special object in spectra, you can take the geometric realization, and now you obtain a spectrum whose homotopy groups will be something very similar to this thing. So one of the major aspects also of Hochschild homology is that it has a circle action. So we have that Hochschild homology has an S1 action. And where this is coming from, you have to look at the superficial structure, and there's something happening. What's happening is that at each level, you have a cyclic group acting on each level. So what are you doing? You're doing what you think you're doing, meaning you're permuting the coordinates using the C2 action or C3 action in such a way that these automorphisms happening at this level are compatible with the faces and degeneracies. Right, so you have a nice coherent structure. So what I mean by that is that if I twist and then multiply and twist again, well, this doesn't make sense here. Well, it's coherent, right? So all these maths work really well. And so you obtain, this will induce an action of the circle. And not only that, is that THH will now have a richer structure coming from having this S1 action. I don't want to say too much about it, but you have stuff called the cyclotonic structure. And it will lead to new invariants built out of the cyclotonic structure, which is induced somehow by the S1 action, which will approximate even better the K theory. So this rich new structure coming from the circle action will be providing new computational tools to compute the K theory. All right, so that was the background I wanted to give on topological Hochschild homology. So perhaps as a motivating of the next step is that this is not any type of simplicial object. We call this type of object with having this extra automorphism acting on each level as being a cyclic object. So let me describe a little bit. that I define lambda to be a category that is an extension of the simplex category, which I call the cyclic category, or cones category, where essentially you have the same first set of maps as in simplex category. So just in simplex category, but now you have this extra maps acting at each level. So So for each element of the group, you'll have maps, which are automorphisms in that category. And it turns out that if X is a functor from lambda up to spectra or whatever, then the geometricization of this guy over delta up, if you do the geometricization of that, this will always have a small action. This is due to the fact that you're factoring through lambda up, meaning you're factoring with this extra set of maps that will provide you always a small action. That's like a general fact. It is in this context that Friedrich-Lodé extended the definition of this phenomenon that is happening here. So, Fyodorovich and Lodé introduced this following definition. So, which would be the main tool of today, which sadly, the examples, I will give you tons of examples, but I won't tell you exactly how they work because it would just take some time. So I hope you will forgive me for that. But let me try to explain. So across simplicial group, that we call delta G. What is it? It is a sequence of groups Gn together such that assembles to a functor in a sequence of groups that define the functor G dot that's going from delta up to set, where you send n to Gn. And you send a map m going to n, call it P. You send it towards a set map from Gn to Gn, we call it C star. So far it's about a group homomorphism. I don't assume that yet. So right now we have set maps. So it's a function like that, together with a number structure. And you have that for any n greater or equal to 0, you have that Gn acts on the set of morphisms and n as follows. Oh, sorry, I'll be done. M n. just introducing a bunch of notation here where phi g is sent to g star of phi. So you have that each gn is acting, producing a new thing, such that, so these are those two structures, and the condition is that the maps phi star and g star preserves composition with crossing. If you know what is a cross homomorphism, this will speak to you. If not, that's okay. So I'll just tell you what it is. So you have phi composite psi. This is g star of phi composed with phi star g star psi, and almost done. Phi star of gh is phi star g multiplied by g star phi star h. So to decipher a bit these two conditions, look at phi star. We would like this to be a group homomorphism. So we would like that phi star g h would be phi star g times phi star h. And it's almost that, except that you don't get exactly phi star of h, but you have to cross to act also on phi to get this. So hence the word crossing here. That's what it means. So let me do examples. So let's try to see if the owl will follow me. So let's do some examples that I want to kind of keep track throughout our examples. So the first one I wanted to make is that any simplicial group G dot is a cross-simplicial group. Because what you have is that the G star will just G will just act trivially on the morphisms, and then this is just a group homomorphism. So every simplicial group is a cross-simplicial group in this way. Another boring one, but I have to say it. You have that delta is a cross-simplicial group, where now it's just a trivial group everywhere. And perhaps you've guessed it already, but lambda is a cross-simplicial group that we call sometimes delta C, with the Gn being Cn plus 1. So you take the cyclic groups, H level, and we have a certain way to act on the morphisms. I should say, perhaps, as an extra data, but some facts. So the fact is that it's generalizing exactly with the thing I erased, which is the fact that delta G defines an extension of delta U simplex category, where you have G0 acting at each level, H1, G2, etc. So you have this extra set of, you should view each Gn as an extra set of automorphisms that are added with your as automorphisms in your simplex category in such a way that they're compatible with faces and degeneracies. So channelful. So that's how you can do it. So it's not enough, let me really be clear, it's not enough for me to just define a sequence of groups and call it a cross-sectional group. I need to really specify, all these maps, right? Which I'm not doing in all my examples because it's a bit involved. But that's the context we are in. So let me do another one. So you have what's sometimes called C, the dihedral category. Where now the sequence of groups will be the dihedral groups. Dn plus 1. So here, I know people use different orderings for the groups. So this, I mean, of order 2n plus 1. Here. So right now I'm just listing a couple of ones we have. We have also Nabla, which is called the quaternionic category. And now the sequence of group are quaternionic groups. So this has order 4n plus 1. Is it okay if I keep going there or over L?
It would go, like it will follow you, yeah.
You will follow me?
Yeah.
Yeah, because I would like to keep them around. There's also delta sigma, the symmetric category. Where now with the GNs, with sigma n plus 1. And okay, maybe the last one. We are all heard, obviously, but something called delta B, which is a graded category. With now Gn being the graded group at level n. I don't know how. Okay, I think they call it Gn. But this is what you have. Another fact that we have. So that was fact number 1. First fact. The second fact is that if you take the geometricalization of this functor here, that's always the topological group. Not only that, plus if X is a functor in from delta G up toward a certain category, let's say, then if you take geometricalization of that functor restricted over delta up, knowing that delta is a subcategory of delta G, take the geometricalization of that, this will have always a G dot action. So that's pretty cool. So let's go back toward here. So, I mean, here will be the usual geometrization of the group. So, I mean, nothing to say. Here, this will be obviously nothing interesting. Here, I will test you that this is the circle. Now, for this guy, here, G dot will be a orthogonal group O2. For here, G dot will be pin minus 2. You know the symbol there, the P2 group. Here it will be contractible. happening here as well. Sometimes you get something interesting, sometimes not necessarily something interesting.
In the last example, is the index on the break group data plus first?
So n,
Is it?
maybe it's n plus 1. Yeah. Yeah. That sounds better. Yeah, so you have all this thing happening. So right now, I've actually not talked about almost half of the title, which is twisted G-rings. But thankfully, that will take me only not too long to talk about. So it turns out that each of these cross-divisional groups will define for you a certain new type of Hochschild homology that will behave well with what I call twisted G-rings, which I'm now going to define. So what is a twisted G-ring? So I'm going to cheat a little bit and just pretend rings are things in abelian groups and not pretend things are in spectra. And hopefully you will like it. So suppose you have a group homomorphism G from G to C2, the second group of order 2, a group homomorphism. So we say a ring R is a twisted G-ring if R is a ring and G acts on R as follows. You have that the induced map by G acting on R is a ring homomorphism if G belongs to the pre-image of 1, so here you C2 as 1 minus 1, or is an anti-ring homomorphism. Otherwise, if G belongs to B minus 1 minus 1. So by anti-ring homomorphism, I mean that it's not a ring homomorphism between R to R, but R up to 1. That is a twisted G. So I'm going to do a bunch of examples, don't worry. So that's it, that's what it is. So obviously every ring is a twisted G ring where G has a trivial group. Obviously any G ring is a twisted G ring where you take trivial group homomorphism. So now it would be interesting to see what type of other things you get on this thing. So I'm going to tell you in a second. But just before that, I want to say how every cross-divisional group has, so any cross-divisional group will fix a certain group homomorphism like this. So any cross-divisional group delta G defines a group homomorphism from G0. And essentially, because each Gn acts on the morphisms, you get that G0 will act on the automorphisms of child with delta, which I can make sense of, and that is C2. I can be extremely explicit of what this group homomorphism is if you want. I'll save it at the end, or for curious people, let's say, if they want to ask at can be described for you. But the point is, any cross-special group will uniquely define a group homomorphism, and that can be extremely explicit of what it does. And so we call this the canonical parity, that's how we call it, of delta G. So let's keep the examples there on the board, and I can maybe talk about what are the, so this, we have twisted G0 rings. Right, so we would like to think what are the twisted G0 rings in each of these examples. So the first one, because I told you that a special group is acting on delta trivially, then what you have is that G0 to C2 is a trivial homomorphism. So in that case, this is just a G0 ring. So twisted G0 ring is just a G0 ring. Here, this is just a ring. So for delta, there's no trivial group, so nothing to do. And same thing for 3. 3 is just a ring. So because G0 is again trivial, it's a cyclic group of order 1. So nothing's happening. So for 4, I'm starting to get interesting. So G0 is C2, and it turns out that the map to C2 is going to be the identity. And so now a twisted G0 ring will be precisely a ring with anti-evolution. So what that means is R together with a map R to R up a ring homomorphism such that when I square it, I get the answer. So ring with anti-evolution. You may have heard this somewhere. For 5, we have that G0 is C4 is the usual closure map to C2. So there, a twisted G0 ring will be a ring with an anti-automorphism of order 4. I don't know the best name, but it's a ring R, and that T going from R up to R is a ring homomorphism such that T to the power 4 is it. I don't think we have a special name, but that's what we have. 6 and 7, they are both trivial again, so it's just a ring. Because G0 is just not interesting in these cases. All right. So now we put things together. And then we can talk about the main construction of our paper. Is that definition, and I'll be slightly hand-wavy, but so suppose delta G is a cross-special group. Then let R be a twisted G0 ring. I guess in spectrum or wherever you want. Let's do it in spectrum. I haven't told you the homotopy coherence with the twisted G0 action, but you can make sense of that. Then we define THG of R to be, well, the same sort of things. Where now you have, it takes a geometrization of that, and now you have G0, G1, G2, etc. acting on it. I guess this has efficiencies. Where now, because this is a geometrization of delta G, of this will have an action given a G dot. I'm slightly lying, so you need, and this is for people familiar with the twists and turns of defining THH with using cyclic category, you need the fact that delta G is anti-dual to itself to make this thing extremely precise. Otherwise, I can still define for you THG. If not, I can define THG. Well, let me just be vague. Let me just be vague. You have a way to define other things, and so you call also TG plus to be the homotopy orbit of the group action of G acting on it. And the point is, if you go back here now, is that you recover the usual notions that you have. So let me perhaps take things in a different order, but let me think of 2 first, or 3 first, actually. Point is, if you take 3 now, if you take delta G plus 2 the cyclic category, then TH lambda is really just the usual THH. So you cover completely the usual definition of topological Hochschild homology using this approach. Number 4, what was it? It was C, the dihedral category. And there, I guess THC, that is THR, so that's what's called real topological Hochschild homology, which is the same type of spectrum as THH, but now you have a richer action of the O2 action happening, where the input is not just a ring, but a ring with the anti-evolution. And so real topological Hochschild homology has been extremely valuable as a refinement of THH. And you also have something called real K-theory, and this provides new tools to really approximate in an even better way. So the point is, if you have a richer structure on your ring, you get more tools to approximate. So we introduce in our paper number 5, really. So if delta G is a quantionic, then TH nabla, how do we call it? I don't think we have a name for it, so we don't have a short thing, but this is what we call hyperreal topological Hochschild homology. And this will now have a pin-2 action. That's a point, but the input will be this weird ring with an anti-automorphism. A word of warning, perhaps it's not super clear, but if you're also knowing all the details in spectra, I didn't say anything about genuineness here. So I should say something. So we don't have anything genuine here. We don't have a genuine action. But in some way, we expect that we can make sense, just in the same way this has cyclotomic structure. People have made sense of a cyclotomic structure on real topological Hochschild homology. They have obtained variation of the topological cyclic factor. You will also expect to have a certain type of cyclotomic or quaternionic, I think it's a better name, structure within here, where you have, again, new approximation tools that you have. And you do need some kind of genuineness coming in at some certain point, and we do expect it to be the case. And it's not clear at all because I didn't really fully define what's happening here. But in these cases, all these are the usual topological Hochschild homology as an underlying spectrum. But that's not always the case at all. And also, it seems that if you look at example perhaps 6 or 7, if you look at them, well, you have the input is just a regular ring, and the output will be just something looking like THH, but with no action. So is that useful? Is that recording any interesting information? And so, yes, it does. So I guess, so it was number 6. So the point I'm making is that TH sigma R has no, I mean, it's acting as a trivial group, so there's nothing super interesting, has no group acting. However, we can still make sense of something like this by taking a certain type of Tor computation. And I can also explain to you, but you can really make sense of T sigma plus R in this case, even though the action is trivial. And this is what we call topological symmetric homology. That looks very different than usual. And for instance, just to give you a taste of what's happening, you have that if you take G to be a finite group, and if you take T sigma plus of sigma infinity plus, which unfortunately has nothing to do with this plus G, this is in suspension of loops Q G. So Q here is looping, I mean the zero space associated with the loop space, and then you just loop it again. So you have like this weird recording happening. And I should say, for this guy, you have that CB plus of the same thing. For instance, this is plus of omega B3. You have this sort of thing happening. Yeah, so this is the current state of affairs. So the hope is that you will get very new interesting structure for particular type of, not every cross sequential group, is equal. It all has the same value, but they will provide different type of information. But we expect that this guy will provide new interesting information, and we expect this to have some kind of connection with floor homology, floor homotopy. That's anything that suits you, because they are looking at things through homotopy invariant things in floor homotopy. And we also expect to define a hyperreal K theory and have a hyperreal trace. Yeah, and I will end there. Thank you.
Any questions from this?
Yes, please.
I have two. So in this quotient, is what you're really doing taking the homology covariance level-wise in the special construction under the GN action?
Oh, not really. I mean, I can tell you what I'm doing. So what's happening is that so how do you usually find THH? By usually, I mean in Nicolas Schulze. You take delta up, you give it inside lambda up, you use lambda, and then you have a certain map going to the envelope of a SOCH, whatever that means, and envelope of spectra, and then you go to spectra. And this is R, and this is something that's lifting somehow. This is a lift of S1, so you're lifting that functor. This map here is a lifting of that functor. And more or less, you can always provide this part in for any cross-efficient group. So what's happening is that for any cross-efficient group, I can define for you a functor from delta G to spectra, which will generalize this. It will not factor through a SOCH, but something which have twisted G rings in the middle, right? So not just rings, but something that records more rich action. But the thing is, if you don't have an anti-duality, which is the case in delta sigma, you do not have an anti-duality business happening, then what you do is being this sphere spectrum viewed as a constant superficial object, and then I view this functor G dot over restricted delta. So that's how I define TGR. So this is like your derived tensor functors. Yeah, that's kind of a Tor thing. And I define TG plus R, but instead of doing over delta, do it delta G. Yeah. So that's one way. And it turns out that if you do this, and if it happens to have an anti-duality, it will be equivalent to the usual definition I provided earlier, where so if you have delta G is equal to delta G of any texture cubization, it will be equivalent to this. The problem is this will not have a G action in general. So when you don't have this anti-duality, you do not know that this even has a G action. So that's why I don't want to call this a homotopy orbit, or I don't think it's fair because we don't even know if it has an action. I don't know fully how to describe this this way, but this is the point of view they have in Federation of Day, where we don't take things topological. We do a certain Tor at this level. Yes, please.
So you mentioned very casually something about hyperreal K theory. So is there some anticipation for what this is, like maybe analogous to Hermitian K theory?
Yeah, I mean, we're expecting some kind of relation to Hermitian K theory, but it's way too early to give you any sensible non-gibberish feedback. So, but yeah, we suspect there should be a notion of hyperreal K theory.
Do you anticipate that this is a general thing, or do you anticipate that this is specific to like the hyperreal case?
So we definitely do need this sort of thing happening. We do need this anti-duality to have this generalization of this trace because, yeah, and to that we know a lot of I mean, I'm more or less given you all them, and a couple of offers, which are a bit of variations of these guys, but yeah, I don't expect there will be much more who have this property. But the other ones are still valuable.
Is there a classification of cross-simplicial groups which have that
No.
property? Okay.
No, it's not.
Okay.
But there's a good classification of cross-simplicial groups. It's like a very well defined, but not with exact property. But in some paper, we studies relationship of delta G with topological Lie group. There's a whole thing about that, and they call these guys like planar cross-simplicial group, and there's a classification with planar Lie groups. I don't know. So there are people who have studied these, but I don't think they claim it, but these are the only ones.
I have another question. So do you expect that you can extract some kind of, cyclotomic E structure in the presence of an anti-involution, or do you need something more specific about the cross-simplicial group?
The E structure you mean?
Sorry?
By E structure you mean?
Sorry, let me just ask the question again. Do you expect there to be some kind of right? So THR and TH nabla are expected to have some kind of quaternionic or like real cyclotomic structure. So do you expect there to be some G analog of that for cross-simplicial groups which admit anti-involution?
Yes.
Okay.
But the thing is, I do not know. Let me just say yes.
Okay. Yeah. Cool. Okay.
But it would have to be case by case study. You have to have a feel of what it should be.
Right.
What's nice about these is that they're really extension of the circle group, so you have a good idea of what it should be.
Right.
Is there any other question from Max? If you're on Zoom, you have a question, just feel free to unmute yourself.
Yeah, I have a question. Do you hear me?
Yeah.
Okay, great. Yeah, so with the topological Hochschild homology, you also have topological cyclic homology kind of automatically coming. Now with, and this is probably because the simplex category has a functor to cons category, right? Right, and so, or maybe the other way around, but because of this direct relation between them. Now, in the case of say the hydro category instead of cons category, or in the case of other twisted crossed simplicial groups that you described, other analogs like with T with this.
Stuff like that.
Yeah, something analogous to cyclic homology.
So the answer is yes. So for real topological Hochschild, this has been introduced. And again, to deduce the topological cyclic homology, you need a cyclotomic structure. So you need to make sense of the cyclotomic structures that I talked about earlier. But yes, the hope is that you get this new invariant using this new cyclotomic structure, and this should happen so this already happens for real topological Hochschild homology, and it should happen for hyperreal topological Hochschild homology. But it should not happen, for example, for the symmetric homology. Yeah,
Have you looked at all at mimicking the construction for like TR? Do we get some sort of new bit vectors?
They should be an analog of TR. So yeah. This requires a lot of machinery actually to say that. So things already get extremely complicated already at this level, and so yeah, so careful handcraftness needs to be happening. But everything that you think is happening in THH in TR should also happen for this game. Essentially, that's the slogan.
All right. So if there is no more question, let's thank Max again for a great talk. And beer. So I assume you're going.